All right. So before we get to the next step of what the structure of atom is, I mentioned, remember, like parallelly, there were so many things being discovered, that were so many things being proved, that some of it reinforced what was already existing, saying, yeah, it fits in with this calculation also, so this particular law is true. And some of it was debunking what was already existing, like, no, this is not correct, we need to improve upon it. So some of the important discoveries that happened before Bohr could formalize the structure of atom is one. The first one is the wave nature of electromagnetic radiation. Okay. So before we get to, okay, what is the wave nature? So what is electromagnetic radiation? So you guys, we have already discussed what is radiation. You guys have put forward like really good points. Most of you associated it with explosions, like it's explosion. Adit mentioned it's related to heat. Yes, radiation is absolutely related to all of it. Radiation is essentially energy. Okay, so energy, light is a form of energy, heat is a form of energy. Now heat, light, all of these are very, very closely related to each other. They're all basically the same form of energy, which is electromagnetic radiation. So if you get down into the details of it, it is right there in the name. So electromagnetic radiation consists of an electro part of it. So it's got an electric field, and a magnet part of it. It's got a magnetic field. So what is electromagnetic radiation? It's basically an electric field and a magnetic field which are arranged perpendicular to each other, and radiation is basically radiating. Radiating matlab it's moving from point A to point B. So that motion of electromagnetic field is perpendicular to both of these. This is very, very close to what you guys have studied as Fleming's left hand rule, Fleming's right hand rule, right? So if you have an electric field and a magnetic field perpendicular to each other, then there is going to be motion of, you know, whatever is there. So all these three fields are perpendicular to each other. So that's how electromagnetic field exists. And this is also the key, like this will show you why is an electric, like why does a magnetic field affect electricity or an electrically charged particle, is because electromagnetic radiation, like electric field and magnetic field are like basically related to each other. They both coexist, right? So Maxwell was the first one to suggest to study it in detail in 1870. He said that when an electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced. That is why if you have moving current, like you have current passing through something, there is always a magnetic field also produced, and the electric field and magnetic field are always perpendicular to each other. So those fields, they're transmitted in the form of transverse waves, and these waves are called electromagnetic waves. So electromagnetic, so you have electric, which is the blue part of it, and magnetic, which is the pink or red part of it. Both of them are perpendicular to each other, and the direction where they move is also perpendicular to both of them. Okay. And when it comes to energy forms that you guys are familiar with, so light waves are associated with oscillating electric and magnetic character. So the light that you see, excuse me, sorry. So the light energy that you guys can see is essentially electromagnetic radiation. Okay. This is like the main point. Energy, especially light energy, is electromagnetic radiation. Now, when it comes to, again, when you talk about electromagnetic fields, it is of the form of a wave. And how much do you guys remember of waves? What do you know about waves? Like, you guys have studied sound waves earlier and waves in general. What all do you guys know about waves? If you don't remember anything, you can say I remember nothing, and then I pick it up from there. But I just want to see how much do you guys remember about waves?
I remember some of the basic terms like frequency and wavelength, but not much.
Absolutely. I mean, they're not extremely basic also. They're quite important characteristics of waves. So Ritu's talked about frequency and wavelength and stuff like that. Very bad drawing of a wave.
I think this is related to sound, but there is high-pitched waves and there is low-pitched wave. So that was also, I think, one of them.
Nice, good try. Pitch is exclusively like it's a characteristic of sound. So it's not applicable to all the waves out there. Ritu has mentioned hertz. Yes. Hertz. Yeah, okay. So you guys are mentioning all these words. I'm glad you guys remember it. Now I just need you guys to put it together.
Hertz is a frequency.
Very good. Yes, Kaveh. So Ritu, you earlier mentioned wavelength and frequency. Hertz is absolutely, it's the SI unit of frequency. So hertz is basically equal to, like I'll tell you what hertz stands for once we talk about the definition. What else do you guys remember about waves?
Trough and crest.
Crest and troughs. Trough. T-R-O-U-G-H. So Adit, what do you mean by a crest? What do you mean by a trough?
Like crest is basically like the highest, highest point that they reach in the wave, like in the graph. Like the highest peak of it is the crest, and the lowest, which goes below the x-axis, is basically the trough.
Yes. So this part is the crest, and this part is the trough. Sorry. Okay. What else? What else?
Amplitude.
Amplitude. Yes, Kaveri. What do you mean by amplitude?
The magnitude, the difference between the distance between the equilibrium and the crest of the trough.
Awesome. Yes. So this distance, like the fact that like this whole thing above this thing is called a crest. From here till the maximum point, this distance is called amplitude. Correct. And amplitude, it is either this distance or this distance. Like both of these are amplitude. It is basically what is the maximum distance or what is the maximum displacement of a particle that is in wave from the mean position. Like if this is the equilibrium or the mean position, what is the maximum distance can it differ by? So it is differing by, it will differ by the same amount above or below, and that maximum distance is called amplitude. Yes. Okay. Okay, so we have discussed wavelength and frequency. Words have come out, right? What do you mean by wavelength?
Distance from one crest to another.
Correct. Very good. So distance from one crest to another. So from this point to this point. So this is wavelength. You can also say from one trough to another. From here to here is also wavelength. You can also define it by the total distance traveled by a wave, like not by the particle, by a wave between, you know, like, okay, it is starting to move from here, comes back, but it's going in different direction, and then comes back to the mean position. So going from here to here, like the distance traveled by the wave as it completes one cycle. So this is like one cycle. This is like another cycle. Or if you take it from a crest, it is starting here, finishes this whole cycle, comes back to the starting point, right? So the distance taken by the wave to complete like one cycle is the wavelength. So wavelength is represented by the Greek alphabet lambda. So this is lambda, basically L in Greek. Okay. L because it's the length. So this is how we write it. This is lambda. What is the SI unit for wavelength?
Centimeter.
Nice. You're on the right track, but that's not the SI unit.
Meter.
Meter is correct. Yes. So wavelength hai na? So if you go by the definition, it's basically distance from one point to another. So how do you measure distance? Meter, centimeter, kilometer, nanometer. So yeah, meters is the SI unit. When it comes to things like electromagnetic radiation, you will come across wavelength being measured commonly in nanometers or angstroms. You guys remember this from the previous chapter? Yeah. So meter is obviously it's the SI unit, but commonly because of the scales, like because of the behavior or existence of electromagnetic radiation, you'll come across it in nanometers and angstroms. Okay. What do you mean by frequency? Start off from the word frequency. Like, you don't have to think about it in terms of
the number of waves.
Waves are
Per second.
and the frequency is more, but the number of waves is and if the number of waves are more then the frequency is less. The number of waves.
Kaveri, I think the earlier you were right. So Rishat and Ritu put together have gotten the right idea, like right definition. It is literally frequency is the number of waves in 1 second. So Kaveri, yeah, going by what you were saying, if the number of waves is more, you can say that, yeah, frequency is more. So let me just write it down. Frequency is the number of waves. So wave, when I say the number of waves, the number of cycles that this goes through. Okay, so this is one cycle, this is one cycle. So if you measure, okay, how many of these cycles is this thing going through in 1 second? So that's the number of waves in 1 second. So that's frequency. So if you were to compare frequencies, the way it looks like, it's basically kind of like this. Draw it here so that it's visible. So let's say this is the point till like 1 second, if this was the time axis. Let's say if there was this wave that's going like this. And there is this wave that's going like this. Call this A, call this B. Which wave has a higher frequency, A or B?
A.
Yes, correct. And which wave has a greater wavelength, A or B?
B.
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 Very correct. Okay. So how do you think, like if the speed was the same, like if they were traveling the same distance in certain amount of time, as long as the speed of the wave is the same, how are wavelength and frequency related? Directly proportional or inversely proportional?
Inversely.
Yes, inversely proportional. So common, like this is important, as long as the speed of the wave is constant. If you're increasing the wavelength, then the frequency decreases, or if you're increasing the frequency, basically you're fitting more waves in same distance at same time, so your wavelength decreases.
What is the SI unit of amplitude?
Amplitude is again distance displacement, right? So SI unit will be the same what you use for distance, meters. Okay. Now frequency SI unit is hertz. What does this hertz stand for? Like in terms of meter, centimeter, second, meter per second, like whatever it may be. What does it stand for? What's the SI unit for frequency?
Meters per second.
How did you work that out, Sanat? Or is that a random guess?
Part guess, part working out, because like it's number of waves per second, so obviously it's gonna be something per second. So I just guessed the meters part because it's distance, right? Kind of.
Distance is explicitly like wavelength. How would you
then
measure?
I don't know.
How would you measure number of something? It's just a number. It doesn't really have units, right? So frequency is
wave per second.
It's just 1 by second. It's second inverse. Second to the power minus 1. That's literally it. Per second. So if I say 50 hertz, so it's like 50 per second. 50 waves per second. Number of waves is 50 per second. So hertz is just 1 by second. That's the unit. That's what it stands for. 1 by s, another way to write it is s power minus second inverse. Second power minus 1. Okay. So these are the different properties or characteristics of a wave. You have wavelength, you have frequency. Another thing, another property of the wave is its speed, speed of the wave. Speed is literally how much distance is it going to travel in 1 second. Okay. So speed is denoted by small. Wavelength is denoted by this Greek letter lambda, right? Frequency is denoted by the Greek letter nu. So in English alphabet, it's N. In Greek, it's called nu. N-U. So it looks kind of like
that A dot.
This one. Oh, this is angstroms.
Okay.
Angstroms is 10 power minus 10 meters. And nanometers is 10 power minus 9 meters.
Ma'am, what is 1 by S? I might have missed it, but what was 1 by S?
Oh, S is basically second. So that's the SI unit of frequency. So it's number of waves per second, right? So that comes in the denominator. So that's what is called hertz. Like when you come across hertz, in SI units, it's actually like 1 by S. Different name for per second. The unit for frequency. And the variable that you use to denote frequency is nu. This looks like V, except it's like imagine there is V blown by a gust of wind towards the left. That's nu. Okay. So how do you think speed, wavelength, and frequency are related?
There was some formula that we learned in the sound chapter.
Yes.
V equal to lambda into nu.
Very good. Correct. So speed is literally how much distance it travels in 1 second, when time equal to 1 second, right? Distance traveled is defined by the wavelength, like how many wavelengths in 1 second. So multiply wavelengths by frequency, you get speed. So this is the formula. V, speed of a wave, is equal to nu lambda. This is an extremely important relation, and yeah, you will use this relation in a lot of numericals. To start off with, we'll solve some direct questions using use this formula. But later on, once we get to Planck's constant and all, like this formula will be used elsewhere. So speed is equal to wavelength into frequency. V equal to nu lambda, frequency into wavelength. Note this. Noted?
1 second.
Okay. Let me know when you guys are ready, okay? So this is a chapter you are literally going to unlock like the secrets of the universe. You'll be like, oh, why do things behave the way they do? You'll come to know in this chapter. Smera is also.
I thought I was getting it, but then I just realized that atoms were immortal.
Did you think atoms could be destroyed or like died or somehow?
I didn't think about it, but I didn't know they were immortal.
Yeah, unless you give like insane amount of energy enough to rip them apart. Yeah, if you leave atoms to do their things, they have survived for billions of years. I mean, they have. That's why we exist. 4 people are done.
We depict electromagnetic radiation in the same way.
Electromagnetic radiation, yeah, like these are the different things used to describe it. Any wave, you describe it using wavelength, frequency, and speed. This is like a simplistic way to denote it. In case of electromagnetic radiation, there's like an additional dimension, like it's traveling this way. Then you have an electric component going this way, up and down, and you have a magnetic component perpendicular. So imagine this is going like in and out of the screen, kind of like that. So the properties like electric and magnetic, they only differ in terms of the direction. So the wavelength is going to be the same, like they intersect at the same point here. Their frequency is going to be the same. The speed at which they travel is going to be the same. Amplitude is going to be the same. Like everything is same. The only way, like they only differ in their direction. Like one component, if it goes in x-axis, the other one's in like y-axis, and then they travel in z-axis, like that.
Ma'am, what does NM stand for? Like in wavelength, like NM.
NM is nanometers.
Oh.
So SI unit is meters, because that's like SI unit. You have kilogram, meter, second, standard. Depending on the context, like because wavelength of electromagnetic radiation is extremely tiny, you measure it in nanometers or angstroms.
Oh, so these are the units then the below.
Yeah. So when you calculate, when you come across readings or when you do numericals, you come across wavelength represented in nanometers or angstroms. So 1 nanometer is like 10 power minus 9 meters, and 1 angstrom is 10 power minus 10 meters.
Ma'am, we can calculate the wavelength by calculating the crest and trough of one wave. Can we also do that?
No. Crest and trough is literally like you say a wave is cresting. So it is in one region related to the equilibrium position. And a wave's trough is in the opposite side of the. It's just like used to describe places on the wave. So there's no like measurement related to crest and trough. The only measurement related to crest and trough is the amplitude. So it shows you how much it is cresting or how much it is like going up. So wavelength and frequency together decide the speed of the wave. Amplitude basically decides the intensity of the wave. So an extremely bright light versus dim light, they can have the same wavelength, same frequency, everything. They differ in their amplitude. Like if you had to talk about it in sound, a loud sound, you can have a loud high-pitched sound and a quiet high-pitched sound. Like the frequency will be the same, but a loud one will have a higher amplitude and a quiet one will have a lesser amplitude. So amplitude basically describes the intensity. So if you're talking about light, an intense light, like really bright light versus dim light. If the color of the light is changing, then yeah, wavelength and frequency are changing. But if the brightness is changing, it's the intensity. Okay. Arnav, you done? Arnav, Shreya, should we move forward? Okay, cool. All right. There's one more characteristic. You guys have learned of this also. Time period. Time period represented by T. Yeah. What do you mean by time period of a wave?
The time it took to complete one wave.
Very good. Correct. So time period is basically how long did it take to complete one wave. Yes, Ritu also said how much time it takes for one wave to get completed. Time taken one wave or one cycle. So time period directly relates to which of these other quantities? Wavelength, frequency, or speed?
Speed? Maybe.
Frequency.
Frequency. Yes, two people have answered. It is the literal opposite of frequency. Frequency fixes the time and then you're measuring number of waves. Time period fixes the number of waves and you're measuring the time. So they both are like inverse of each other. Okay. So what's the SI unit for time period?
Seconds.
Second, absolutely. So you can see it in the SI units also. Time period is second and frequency is like 1/2. So T is equal to 1/nu or nu is equal to 1/t. So this is the relation between time period and frequency. So in case you're given the time period but not the frequency, then you know how it relates. You can figure out the frequency. Sometimes you won't be told the time period, you'll be described that, oh, it completes 8 into 10 power 10 in 1 second. So based on that, you have to figure out what is the frequency and do the calculations. Okay. Oh, there's one more aspect to it. Characteristic. there's something called the wave number. So wave number is represented by nu bar. So just nu is frequency. If there is a bar over it, nu bar, that's wave number. Can anyone like try and figure out what wave number can be? What it would be?
Number of waves in a given time period.
Number of waves in given time period is frequency, right?
I think wave number is the reciprocal of wavelength.
Yes, Kaveri, correct. So relation is yes. So wave number is the reciprocal of wavelength. So if you had to describe it or define it, what is your understanding of this? Start from definition of wavelength. So wavelength is how much distance does the wave travel to complete one wave. So if wave number is reciprocal of it, how would you twist that?
Could you repeat wavelength ka definition?
Yeah, wavelength is the distance traveled by one wave, or distance traveled when a wave completes one cycle.
I guess in 1 unit of distance, how many waves?
Absolutely, that's all it is. So wave number is basically the number of waves or number of cycles completed in 1 unit of distance. So because in 1 unit, you're checking the number of waves, iska SI unit is basically meter inverse. So it is inverse. So other ways of measuring it is centimeter inverse, or yeah. So this is the SI unit. So meter inverse basically equal to 1 by meter. So number of waves in 1 unit of distance. I mean, that's what the word literally says. Like, what is the wave number of waves? Is that is 1 unit of distance. So in 1 meter, how many waves exist? Or in 1 centimeter, how many waves do you find? Clear?
Yes.
Let me know when you guys are done with this.
I just had.
Okay.
Go ahead, Kaveri.
No, you're gone. It's not related to this chapter.
Okay, ma'am. So in the start, we were, learning about the structure of atom and stuff, and now we're learning about waves. So what exactly is the chapter about?
So the chapter is about the structure of atom. We're learning about electromagnetic radiation because there's some phenomenon related to how light behaves, like how it interacts with the atom, how it interacts with the electrons. That tells you something about the structure of atom. So you need to have this knowledge in order to proceed forward. Otherwise, it's not going to make sense. That's basically it.
Ma'am?
Yeah?
This is like, I have a slight clarification related to the last chapter. So in the Avogadro's law, it was the mole volume was 22.4, right? But today, at STP. But today, when we were doing the same chapter in class, I think ma'am said something about NTP, and I didn't get what that was.
Oh, that's a good question. Can you remind me, like, once we are done with the chapter, or like kind of taking a break? Or I'll just like finish discussing this. Let's go at a logical checkpoint, and then I'll clarify that. Okay. Okay. So wave number, so different aspects of a wave. So you have wavelength, frequency, speed, time period, wave number. So time period and wave number are basically related to wavelength and frequency. They give the same aspect of a wave, just described in different ways. Wavelength and frequency together, when you multiply them, you can figure out what is the speed of a wave. Okay. So these are like the three main quantities to figure out the wave. This is an important relation. Now coming back to electromagnetic waves, I told you that light is basically an electromagnetic wave. Like light is a form of electromagnetic wave, at least visible light as you know it. What do you know about light? Like what all aspects do you know about light so far? Come on guys, you can like mention whatever you know about light. Like you don't have to worry about what are we talking about.
Speed of light in air is 3 × 10.
Very nice. So there's stuff about the speed of light. Is this so speed of light in vacuum, does the speed of light change or is it like a constant?
Constant.
Yes, speed of light is 3 × 10⁸ meters per second, and this is a constant, so it is represented by the variable c. Speed of light is c. This is a universal constant. This doesn't change anywhere in the universe. In vacuum, it is 3 × 10⁸ meters per second. In air, it's pretty much the same thing. Approximately it's like 2.998 something. All right. In other medium, yes, based on refraction, like based on the refractive index, it changes the speed. But that's only because it's behaving, it's interacting with the molecules or atoms that are there in substances. Okay. So light is a form of electromagnetic radiation, right? And the speed is constant. Now, this particular value, c, because it's a wave, you know that we can express it in the form of nu lambda, which means that the frequency and the wavelength may change such that when you multiply them, they always have to be a constant, which is this particular number. So based on how the frequency is changing, electromagnetic radiation is of different forms. So you call that the electromagnetic spectrum. So spectrum meaning it's like a whole range of things. So you can see over here. Is the image clear, or should I look for a bigger image?
Yes, it's visible.
Visible? Okay. So let me just open this. Okay. So you can see here. Now the frequency and the wavelength will change with respect to each other such that the speed is always the same. So depending on the values of, either frequency or wavelength, you can pick any one. Electromagnetic radiation is of different, different types. So short wavelength meaning higher frequency that corresponds to higher energy waves or higher energy radiation is first you have gamma rays. as the wavelength slowly increases, you have X-rays, and then you have ultraviolet rays. Visible is a tiny range. So it's called visible because it is visible to human eyes. And then you have infrared radiation, and then you have microwaves, and then you have radio waves. So there's like definite values associated with it. Let me see. Oh yeah, you're given the values also over here. So you can see that 0.0001. So these are the values of wavelength that is given. So when the wavelength is so small, the frequency is extremely high. You can see how the visual representation of the wave is also changing. So that consists of gamma rays. Then between 0.01 nanometers to 10 nanometers, you have X-rays. So this is what are the rays that you use in medical testing. Now, because they have such a short wavelength and they have extremely high energy, that is the reason they are able to pass through the soft areas of your body. Okay, so yeah, bones, like really dense things like bones and teeth and all are able to stop X-rays, but the soft tissue, the flesh that you have, like the muscles and the fats and all of that, X-rays are able to pass through them, which is why they're able to do that. And that is the reason X-ray technicians stand a little far away and you have all that protective equipment, because high energy waves actually affect the atoms, like individual atoms of your body. And yeah, that's why they have a tendency to destroy. That's why you need to be careful. But if you're taking, if you're taking X-ray like once a year, once in a while, only when you break your bones or something, it is completely fine. But if you're like standing near X-rays like all day, every day, then it's going to harm your body. Because these are like pure energy particles. Then comes ultraviolet. Ultraviolet, because these have energies beyond the violet. So you have a tiny strip of visible light. This is what you can see. This is what you perceive as light, like when things are lit, that you can see as different colors, all of that. Beyond violet, humans can't see ultraviolet. There are some animals that can see these wavelengths, but us humans cannot see it. But yeah, this is also electromagnetic radiation, just that the frequency and the wavelength are different. So yeah, Kaveri?
Gamma rays and X-rays, do they have a color?
I mean, color is defined only because we humans can see different colors and we put names to it. When you can't see what ultraviolet, X-rays and gamma rays look like, it's difficult to describe it in terms of color. See, when you get right down to the physics of it, the range, this particular range of 400 something nanometers to 700 something nanometers is what you can see. When you look at it from the light's point of view, from electromagnetic radiation's point of view, it's all energy. The only point of difference is the frequency, either frequency and obviously along with it the wavelength. So beyond 400 nanometers, humans cannot see it, but it is still energy. It is still something that affects us, right? So X-rays affect us in different, like we are able to take X-rays because they pass through some parts of our body and they don't pass through other parts of our body. Gamma rays are really, really difficult. This is what you find in space, which is why you need space suits and like really special materials when you go up in space in spaceships. If you put a human out in space with just an oxygen tank without any protective gear, they're going to literally burn to it. Like it affects like really high. See, imagine heat is a form of energy, right? If you put your hand on top of a flame, how does it feel? Like what happens to your hand?
We feel hot and it probably burns.
Probably it burns, right? Beyond like a certain temperature. Temperature representative of energy. So higher the energy is, more it's going to burn. Similarly, why do you apply sunscreen?
So that we don't get tan.
What causes the tan?
The UV rays.
UV rays. And visible light doesn't really cause tan, but UV rays causes tan because UV rays are of a higher energy than visible light. So they have enough energy to make your molecules, the molecules that are present in your skin, react in a certain way. Like you give it sufficient energy, they react in a certain way, and that causes like cancer and sunburns and all of that, right? So X-rays are again really harmful, which is why like when you take X-rays, when you have a fracture or something, that 1 minute or like a few minutes that you're standing in front of the machine is all right, but you can't be exposed to X-rays for like hours together. So like imagine an intense form of getting sunburned. And gamma rays are 1,000 times worse than like UV rays. Almost 10,000 times worse than UV rays. So such high energies is going to it's going to like literally break apart the molecules that make you, that destroy you. So yeah, that's the reason when you go out in space, you need all sorts of protection. You're getting protected from the gamma rays that exist in space. So
ma'am.
Yeah.
So I guess you said we cannot see beyond 400 nanometers, right?
Less than 400 nanometer and greater than 700 nanometer. So between 400 to 700 is the sweet spot. That's the only part we can see.
Okay.
So visible light you can see, and depending on the wavelength, you can perceive different colors. Lower wavelength is like violets, blues, then slowly getting bigger, you have like yellows and then oranges and then red. This is your Vibgyor. Okay. This is what rainbows are doing. This is what a prism does. So your visible light, all of them together, you see it as white light. But yeah, like when you split them up, they're being split on the basis of their wavelengths, which is why Vibgyor is always Vibgyor. You can't mix it. Like those colors are not mixed up. Then beyond 700, greater than 700, lower in energy, you have infrared. This is what contributes to temperature. In fact, that's how infrared rays were discovered. They were discovered by Newton. So Newton was doing experiments on light, right? Like you had the particle nature of, like he was the one who proposed particle nature of light, I think, and he had given like a color theory and all. The reason why he was able to do all of that was because he was experimenting with prisms. So what he did is, Newton and Huygens, I think, it's one of them for sure, like one of the people who were trying to figure out light. So this was when the colors were like, they were trying to figure out, okay, prism takes in white light, splits them up into different colors. Now, what is the significance of this? Like they were trying to figure out why does the splitting happen and what is different in the case of all of these things. So one of the things they suspected was, are the temperatures different? So what they did is, like they took a prism, sunlight, they split it into different colors, and then they put a thermometer at different places, trying to see if the temperature of each color is different. Is that an aspect of the difference? And along with all these temperatures in the different colors, they put another thermometer beyond red. Like red color ended till here, and then they put a different thermometer as a control, like, okay, atmospheric temperature. Is it increasing compared to the atmosphere, decreasing compared to like your normal regular room temperature? They wanted something to measure it against. So this is the control. But what they found out is the thermometer beyond red, this started showing like higher temperature. So that's how they figured out that, oh, the 7 colors are not the only aspects of light. There's something beyond the 7 colors that we can't see. So sunlight that you get, you're getting it over a whole range of wavelengths. You can only see a tiny narrow strip over here from 400 to 700, but all of these are also existing, which, all these different machines are able to detect. Now, because it is beyond red, something you can't perceive, they called it infrared, IR radiation. So this IR radiation is what contributes to heat, like you can feel it as heat, basically. And yeah, this particular range is called ultraviolet, is because violet you can see, and it is something beyond violet, so it is ultraviolet. So yeah, so more than 700 nanometers, you have infrared in terms of wavelength. Then beyond infrared, still these are all lower energy. You have radio waves. So these are the waves that they're literally called radio waves, TV rays. Like these are what your radios work on. Like this is the frequency or wavelength at which your TV signals is passed. Like you have the dish TV, right? So the dish is detecting wavelengths at beyond like 1 centimeter, 2 centimeters on your FM, AM. This is how signals work. There's microwaves also. Like microwaves, again, you have microwaves at home, right? Microwaves also, I think they fall between gamma rays and X-rays, somewhere over here, I guess. Their spectrum is somewhere over here, the spectrum. But yeah, microwaves, you have all these rumors of, it's dangerous and all that, because again, they are higher energy waves. And that's the reason you can't put metal in the microwave, is because the energy is enough that it makes the metal atoms react, and that's why you have all these fireworks inside. And that's how microwaves heat food also. It heats food by literally giving it pure energy. So yeah, so this is the electromagnetic spectrum, and the spectrum differs.
Microwave is that high?
One moment. Okay. So this is how
whatever below the visible light, that is harmful, I guess.
Yeah. So beyond ultraviolet, like none of this is visible. The only visible part is this tiny, tiny little range. Everything beyond this is not visible. Everything beyond this is not visible. But yeah, higher energy, like beyond violet, this is harmful.
And infrared is just like the normal heat.
Heat, yes. You feel it in the form of heat. You can't see it, but yeah. So when you say heat energy radiating out of like a hot substance, it's basically radiation at infrared frequency. Yeah, Ritu.
You said like beyond red, the energy decreases. So when they put like the thermometer, then why did like the temperature increase?
Over the whole scheme, like over this whole electromagnetic radiation, this is like highest energy, and this is like lowest energy. You're talking about this thermometer. Well, compared
Shouldn't
to
the temperature have reduced?
No, because infrared still exists, right? So this is what we are detecting in the form of heat. So compared to, let's say, room temperature that you have normally, if you're not concentrating like any sort of sunlight over it, then you have like a certain temperature, because you're like this. Remember, all these experiments are performed in a room, and there's like a single window that allows light in so that nothing is contaminated and stuff. So it's all shaded. Inside shade, it exists at a certain temperature, this room temperature. Now you're letting light in. It's splitting into different colors, yes. And there is infrared also that is being split, like along with the different colors. So infrared also exists beyond red at this point. So compared to room temperature, what they expected is they didn't see light over here because prism only visible range was visible. So they expected this to behave like a thermometer that exists anywhere else in the dark shaded room. But it did not behave that way. Like it showed like a slightly higher temperature compared to what the scientists were expecting. So that's how they could detect that, oh, this is not empty. There is something coming from sunlight over here. So beyond red, there is still some sort of radiation that is enabling the temperature. That was how it happened. So yeah, this is the electromagnetic spectrum. So your light, heat, like any form of energy, pure energy is electromagnetic radiation. You can perceive, like humans can perceive this tiny window between 400 to 700 nanometers. There are animals, like I think it's a form of shrimp that can perceive beyond what humans can see. Like of course animals can detect. Plants need ultraviolet light, like they absorb light in the blue and red range, which is why chlorophyll is green in color. This is what it reflects. So yeah, living organisms make use of different parts of this whole spectrum. We ourselves, even though we can't see, because we studied, we know of their existence, we make use of X-rays, we make use of the microwaves, we make use of the radio waves. But yeah, like next time you come across things like these, put it in context. Like they're all electromagnetic radiation. They're just changing in terms of their energy. And I'm sorry, I wrote it wrong. Energy changes with frequency. Like higher frequency means higher energy. So this side is
directly proportional.
Oh wait, I wrote it correctly. The arrow confused me basically. Yeah, this side is high energy, this is lower energy. So energy is increasing from right to left. Lower wavelength is higher frequency, and higher frequency means higher energy. Higher wavelength is lower frequency means lower energy. Okay. Ritu, higher the energy, higher the temperature, right? Again, when you're talking about temperature, you get into some, like it's not just radiation. Temperature is not radiation. So temperature is measurable only when it relates to an object. Like you can't measure the temperature of space. You need something there to measure the temperature of, because temperature directly measures with what speed the atoms or molecules making up that particle vibrate.
Ma'am, I have a question.
Yes.
So, like, I wanted to ask it when we were talking about the tanning thing, but like I forgot.
Okay.
So, like, how humans they get tanned now when they come into contact with UV for a long period of time. So, do animals and plants does that also happen with them, or like
Yeah, of
something
course.
similar?
I mean, maybe not tanning. Like maybe we don't call it tanning because animals have fur, like they don't have skin, like we can't see their skin getting changing color as such. Plants obviously they're like completely different, they don't have skin for anything at all. But yeah, so plants they can photosynthesize only because like they're making use of the UV rays, right? Animals also, I'm sure they must be making use of some aspect of the spectrum. Like for example, like there is some shrimp, like I have to do some research about it. Like I've read about it a long time ago, but I forgot. They can, like we can see only in visible range. Shrimp can see a lot, not all shrimp, like there's a particular species that can see a greater range, which means they can perceive more colors than us. And we never know what they will look at it as because yeah, we can't, we just, our eyes don't have the ability. And Arctic foxes, they are pure white in winter, but they take on darker colors in the summer. Now that change obviously must be stimulated by change in temperature, because winter temperature, summer temperature. Maybe the exposure, again, temperature is affected by the exposure to sunlight. So they must be reacting to something. So yeah, like definitely everything is affected by the rays, just in different scales. And it also depends on the biology. Like how are they equipped to handle that? Like sometimes there is no effect at all. Sometimes if something is sensitive to light, then yes, throwing light on it, like exposing it to certain amount of radiation is going to affect it.
Yeah, like the severity can also be different.
Exactly. Yeah.
Okay, ma'am. Thank you.
Rishit is asking, can you once again explain the experiment of Einstein? No, we haven't discussed the experiment of Einstein, Rishit. Like this experiment, it was basically just the discovery of infrared. So if you want, like, I just told it to you in a rough way, but I'm sure there exist videos or written documents. Just Google discovery of IR. Basically, the idea is that they used a prism to split the 7 colors. At that time, they just knew that there were 7 colors, but in fact, the reality is that there's wavelengths beyond the 7 colors, and that they could detect because of change in temperature. And that's how they discovered the infrared. Yeah, Kaveri?
What is 100-meter AM?
Oh, this is the, like, are you familiar with AM radio, like FM radio, AM radio?
Yes, ma'am.
Yeah, so that 100 meters is the wavelength at which AM radio signals work. So, how many of you have seen the old-timey transistors or radios, like where you have a knob and then you're dialing, like changing the knob? I think even in cars you have it, right? Like if you're trying to work the radio, you're like changing it through the different channels. Yeah. So what you're doing is you are tuning the not the transmitter, receiver. Receiver that is present in the radio to be sensitive to a certain wavelength of the electromagnetic spectrum. So yeah.
Because like every channel has their own wavelength, right?
Correct. Their
like
own
that's
frequency.
Why every channel is like 91.9 FM.
Correct. So it's
that's
in the FM range, and their unit, like their value, I can't remember if it is like frequency or wavelength. Yeah, so that value is 91.9, 97.6. So FM is a more modern thing. So FM came about when I was in high school. So that was like early 2000s, like just when you guys were like born. Just before you guys were born, I guess. Before that, like back in the 80s, 70s and all, radio worked on AM frequencies. So yeah.
What exactly is a AM frequency? I have always seen it in FMs and AM. I mean in the radio, but I've never known what it is. So can you just tell what it is?
I have to do, like, I haven't really, not very well versed in the workings of a radio, so I have to do research.
How does the transmission work? Like, do you just broadcast it from somewhere like really high?
Yes. So
I think the antenna has like a machine, and that produces a frequency.
Correct. That doesn't produce it as such. Like,
but like it conveys it.
Yes. No. The antenna that you have in your radios is connected to the receiver. So that's why when you change the direction of when you adjust the antenna, some places you get a better signal, other places you don't get a better signal.
I was talking about the one at the
frequency doesn't change.
Broadcasting area, like where they broadcast.
Broadcasting area, yeah, that place it transmits. So you have something called radio towers, right? It looks something like this.
Yes, ma'am.
Like you have whatever, like towers, and then at the top you have like a dish sort of a thing.
A dish, yeah.
Yeah. So radio towers. So this transmits. So this basically transmits out into the world, and there's like satellites revolving all over. So it goes from radio tower to satellite, and satellite to whoever is willing to receive it, whoever has their transistor or radio on at that point of time.
Ma'am,
yeah,
I have like a radio-related question. When we turn the thing, change the frequency, sometimes we hear nothing. We hear that disturbance noise.
Yeah.
So what is that?
Static.
That's static. So at that frequency, nobody is transmitting any data at all. Like there's no sound present. So that's like static. That's basically nothing. Pure energy.
I think static is like used to fill the void.
Yeah.
Like not exactly void, but like it's a rough explanation of that.
Yes.
It doesn't the frequency change if you're like transmitting it from like space?
The frequency remains the same. Like that's what all these devices do, right? It's not just like bouncing off like mirrors. They're not mirrors. So they are literal transmitters. So their only work is to catch these signals and throw them the exact same way without changing much. So there you go. FM stands for frequency modulation.
What if the frequency from two different sources is the same? Like
it's going to be garbled, and like there's going to be conflict there, which is why different radio channels have different frequencies associated with them. You can't have it at the same time. Adit is asking if humans come in contact with gamma rays, will the encounter be extremely painful and quick, or will it take time? I don't know, Adit. I'll have to do the research on this. Or even if I've come across it, I don't remember at this point of time.
Didn't gamma rays create the Hulk?
Yeah, that's fiction. That's not fact. It's not scientific. It's fiction.
Was that painful?
I don't know.
In theory?
In theory, it is going to be painful, but how long it's going to take, I think it would also depend on how you're exposed to it, right? Is it like a large amount of radiation all at once, or is it like slowly seeping through? If it is like a slow thing, then yeah. If it is all at once, it's going to be really quick. If it is like slowly seeping through, like if you're going out in the sun without sunscreen, if you're getting sunburned, it takes a lifetime. First you develop cancer, like skin cancer, cancer in other parts, which is obviously extremely painful. So it also depends on how you're exposed to it. All right, coming back to electromagnetic spectrum, I'm so glad you guys are asking all these questions. It means that you're actually, yeah, good stuff. I appreciate this for this. Okay, so the kind of numericals, okay, coming back, okay, do you guys remember what we actually studied? What is wavelength, what is frequency, speed, how they're related, all of that? Okay, so numericals, look at an example, like see how to solve these problems, and then you guys can try solving on your own. The Vivid Bharati station of All India Radio Delhi broadcasts on a frequency of these many kilohertz. So if you see a small k before any unit, stands for kilo. Kg is kilograms, km is kilometer. kHz is kilohertz. Okay. So this is the frequency. Calculate the wavelength of electromagnetic radiation emitted by the transmitter. And which part of the electromagnetic spectrum does it belong to? So let's do the first part of the question. So what information are you given in the question? Like always start off by trying to interpret the question. So what information are you given here?
Frequency.
Frequency, yes. So you're given frequency equal to 1368 kilohertz. When you're writing the given information, always convert it into SI unit. That way you won't make like silly mistakes later on. If your units are all uniform, things are clear. So this you can write it as 1368 into 10 cube hertz. All right. What are you asked to find out?
Electromagnetic
The wavelength.
wavelength, basically. Yeah.
Wavelength.
Yes. Yes. Lambda equal to how much? How would you relate frequency and wavelength? Like what formula do you have to use?
Constant is equal to d into lambda.
One correction, the C is not constant. This stands for the speed of light or speed of electromagnetic radiation. Okay. Speed C equal to E into lambda. So calculate and figure out what is the wavelength. Yeah, this is like one of the chapters that's going to have insane calculations, weird calculations, purely because you have to deal with like these kind of constant values. Okay. Kaveri, always send your answer with the units, okay? Because I'm confused. I don't know if that's meters or nanometers or what exactly is it. Also, that is not the right answer based on what is given here. Check your calculation. Your division.
Excuse me, ma'am. What does HTS mean?
How to solve.
Like,
The
okay.
code is how to solve. Solve example. Like it's showing you how to solve it. So first couple of questions, you guys can use a calculator because I want you guys to focus on how to do a question rather than get bogged down by calculations. Once you get in the zone, when you are doing the homework, then yeah, do it without calculator. Okay, again, I think I mentioned this last time. If you're getting something like 1 to 3 into 10 power something, always change it as 1.23 this format. And if it's like a simple thing, if you're getting 1.23 into 10 square, then you can write it as 123 easy enough. Only when it's like an extremely large or small number, then change it. Okay. Rishit, yes, but close to the right answer. Smera, yes, you got it exactly right. Kaveri, check your calculation. The number itself doesn't look right. Kaveri, you only told how to approach the question. Where do you go wrong? You need to check your calculation, basically, the mathematics part of it. Ritu, can you use a calculator and tell me how much that comes out to? Rishit, close enough. That's not extremely accurate, but because you rounded it off less than this thing. Yeah, I'll accept that. It's not accurate, but it is closer. Ritu, use a calculator, no issues. Sanat, Arnav, Shreya, Adat. Yes, send it. Now you got closer to the actual value, Kaveri. Yes. Ritu, yes, correct. Shreya, absolutely. Again, units, guys, units. Adat, correct. Okay, I think most of you have gotten it. Yeah. So use the formula. So lambda equal to C upon, this is supposed to be new, but because fonts and all that, it's stylized version of new. But yeah, you divide 3 into 10 power 8 upon 1368 into 10 power. This needs to be 10 cube, not 10 power minus 10. So yeah, once you divide both of these, you get your answer. So which part of the electromagnetic spectrum does it belong to? So once you get your answer, just compare it to where it falls in the spectrum.
Gamma ray.
Ultraviolet rays.
Okay. What wavelength did you guys get?
Radio wave.
You got 200
Radio.
something meters, no?
Sorry, meters.
Oh, that's meters. Yeah, it's a radio wave.
Radio, infrared.
Infrared. Here you got it. Meters. 10 square meters is AM. You've come to radio waves. This falls in the radio waves. 200. 2 into 10 square. So radio wave stage. Yeah, like that was a huge clue. It says Vivek Bharati All India Radio. So, yeah. All right. So you have questions of a similar nature. Calculate the wave number and frequency. So these kind of questions. So now you guys have the basics of electromagnetic radiation, what they are pure energy. Now how it relates to the structure of atom, like how it relates with matter is, we'll take this up in the next class. All this is like new stuff you guys are going to learn about. We are into some quantum mechanics this chapter. In the meantime, yeah, so Kaveri, you asked about NTP, right?